This lecture will deal with Module 3 and Section 3.1 of Chapter 3, which is Graphing and Maximum Minimum Problems. So today we are going to just discuss some functions which are continuous and not continuous at some points, and also some results related to continuous functions. So differentiation is a concept which helps us to understand more about functions and how the functions lean and how the functions bend when we are looking at the graph of a function. So to talk about continuity, we know that a function f of x is said to be a continuous function at the point x naught. At the point x naught, if limit x tends to x naught, f of x is equal to f of x naught. We have dealt with the definition in the earlier sections. And a function is said to be continuous on the entire given interval if it is continuous at every point on that interval. So that's how we define a continuous function. So usually if the domain is R, suppose if we are defining a function from R to R, we say that the function is continuous on the whole real line when the continuity is happening at every point inside the set of all real numbers, and then we say that f is continuous. And for making it as an imprecise definition, we can say that a graph which is drawn on the xy plane such that we can draw the graph without removing the pencil from the paper. If it is so, then we can say that the function is continuous. So you can see in the next figure, you can see two functions which are drawn on the xy plane, and you can see a point x naught here. So the corresponding function's value will be here. This will be f of x naught, right? And the point is the ordered pair x naught y naught, where y naught is equal to f of x naught. And here the function, when it is drawn in the xy axis, with respect to the xy axis, we can see that the function can be drawn with our medium without erasing our pen or pencil from the paper. So this is a continuous function. And when we are considering the second example, you can see that at x naught, the function is jumping off to some other point. Okay, so here we can say that limit x tends to x naught minus f of x is existing. That is, the left limit is existing, and that limit value will be the point here. Okay, and also the limit x tends to x naught plus f of x also exists. The limit value will be coming to the point here. This is the right limit, and this will be the left limit. Okay, so you are seeing two functions such that the first function is continuous at, it is continuous, you can see that it is continuous at every point which is considered, and in particular it is continuous at x naught. But here this function which is drawn is not continuous at x naught. Now we are going to see some examples and understand how the continuity at each point of the domain is. So we can see the first figure, and here you can understand that at this minus 2, the function was going like this, and when it reaches the point here, it suddenly jumps to another value here, and then it is going like this, and at -1 the function is jumping like this. It is going continuous till here, and then at 0 it is jumping to this point, and so on. So the jumping is happening at each of the integer values, that is minus etc, -3, -2, -1, 0, 1, 2, 3, etc. It is going on like that. The function is clearly defined on the whole real line. Okay, so this function jumps in at each of the points. X naught is equal to 0, x naught is equal to plus or minus 1, x naught is equal to plus or minus 2, and so on. So limit x tends to x naught, f of x does not exist at these points. Why? Because we had seen how we will understand it. See, at -2. Suppose at -2 we are approaching from the left and from the right. So from the left, when we are considering the function is moving on to here. And when we are considering the function from the right, the function moves to this point. From the left, the function moves to this point, and they are not coinciding. So that means the function is not continuous at -2. Similarly, the same thing can be justified at -1. So at -1, if we are moving from the left, the function correspondingly moves to this point, and if we are moving from the right, the function is moving to this point, and both of them are not coinciding. So that means it is not continuous at -1, 2, and the same justification can be applied for the points -2, -1, 0, 1, 2, 3, and so on. So here -3 and so on. This is happening like that. So in the explanation, in the solution, you can see that the first function is jumping at the points 0, plus or minus 1, plus or minus 2, and so on. So limit x tends to x naught, f of x will not exist at these points, but the left limit and right limit exist. They will not coincide with each other, and thus f is not continuous at those points. However, f will be continuous on each of the intervals between the jump points, because if this is -3, you know that from -3 to -2 it is continuous. Then only the jump is happening. So you can claim that f is not continuous at the points x naught is equal to 0, x naught is equal to plus or minus 1, x naught is equal to plus or minus 2, plus or minus 3, plus or minus 4, and so on. But we can claim that f is continuous inside every point continuous at every point inside the intervals, say -3, -2, -2, -1, -1, 0, 0, 1, 1, 2, and so on. So this function is continuous, or you can even say closed interval, -2, -3, -2, -2, -1, -1, 0, 0, 1, 1, 2, and so on. So f is continuous on each of the intervals between the jump points. This is what which is meant by this statement. And as you can see, the second example, the function given is drawn in the figure. as a figure. And when you are looking at the figure, you can understand that if you're moving from the left of -1, if you're moving from the right of -1, the corresponding function values will be moving from the left like this and from the right like this, and they are not coinciding. So that you can understand that at -1 the function is not continuous. And the next one is the point, call it 1. Okay, if this is 1, if you're moving from the left, if you're moving from the right, the corresponding function is moving like this. The function is moving like this from the left, and the function is moving like this from the right. So that means the left and right limits are not coinciding. That will mean the function is also not continuous at 1. Okay, so as an explanation, you can read the solution. This function jumps in at the value x naught is equal to -1. You can see the function was very continuously moving like this, and at -1 suddenly it is jumping to some other point, and then again the function is moving very nicely. We can draw it without lifting our pen or pencil, and then at the point +1 again the function is jumping, and then again it is moving very continuously. So to be very precise, we can see that the function is not continuous at x naught is equal to -1, as well as it is not continuous at x naught is equal to +1. That means limit x tends to +1 f of x and limit x tends to -1 f of x do not exist, because the left and right limits of those points are not existing. Thus, f is not continuous at x naught is equal to plus or -1 because of the jump. And also we can add by saying that the function is continuous on each of the intervals: -∞, open interval, -∞, -1, also open interval -1, 1, and open interval 1, infinity. So the parts of the function are continuous. This much function is continuous, this part is continuous, and this part is continuous. So you are just partitioning the domain into the 3 subintervals in which the function is continuous. And if you are looking at the third question, this function can be drawn without lifting our pen or pencil, and clearly that means the function is continuous, though it has very sharp corners. The corners are here 1, 2, 3, 4, 5, 6, like that. It has sharp corners, but still it is continuous. It is continuous because limit x tends to x naught, f of x is equal to f of x naught at each point x naught. So that is the definition of continuity at a point, and that is satisfied here. And what about the fourth question? The graph is drawn, and you know that the function is moving like that very continuously till the point 1, and at 1 the function jumps to some other value, and then again it is moving like this. Okay, so we are looking from the left, from the right of 1. Similarly, we are looking at the function's movement from the left and from the right, and you understand that this is the value to which the left and right limits are tending. That means this is the limit of the value of the function at 1. So that's what which is given in the explanation 2. Limit x tends to 1, f of x is equal to 1, because here it is given to be 1. This value is 1. So the limit is existing, but we know that the limit is not equal to f of 1, because f of 1 is equal to 2, right? F of 1 is equal to 2. So you get that limit x tends to 1, f of x is equal to 1, but which is not equal to f of 1. That is an observation. you can get from there. So, and this will mean that the function is not continuous at that point. And also you can split up the subintervals and say that where the function is continuous. It is continuous on the intervals minus infinity, 1, as well as the open interval 1 infinity. So this is an inference from the 4 graphs which are given in example 1. And another important recap we need is that a rational function is continuous at points where its denominators do not vanish. A rational function is nothing but a function which can be written as p of x by q of x, where p of x and q of x are uh, any functions of x. And whenever q of x is not equal to 0, we can say that f of x is continuous. That's the criteria of a rational function to be continuous. A rational function. So this is a rational function such that q of x is not equal to 0 will imply f of x is continuous. So that's what this statement will mean. Now example 2, show that the function f of x is equal to x minus 1 by 3x squared is continuous at x naught is equal to 4. So the solution, you understand that this is a rational function because you have a numerator and denominator, and we are looking at the continuity of the function at x naught is equal to 4. So when you substitute x naught is equal to 4 for this function, you understand that the denominator is not vanishing, right? That is, suppose if we put x is equal to 4, you get 4 minus 1 divided by 3 into 4 square. And you understand that 3 into 4 square is not equal to 0. So, since this is a rational function such that the denominator is not vanishing at that point, that will mean the given function is continuous. How? Because of the rational function rule. The rational function rule is the statement which we have underlined here. The next example is about step function. Step function, the name of the function comes from how its graph look like. Suppose if you have 0 here, see the g of x is defined as whenever x is less than 0, g of x will be 0 like this. And whenever x is strictly greater than 1, you will have a value to be 1. So it is looking like a step. That's why it's called a step function. Here we are saying that g is not continuous at the point where it jumps. So from the early examples, you are understanding that whenever there is a jump occurring, there is a difficulty for being continuous, or we can say that at that jump the function is not continuous. So here the jumping is occurring at the value 0. When we are moving from the left and from the right, the function is moving towards 0 from the left, and the function is moving towards 1 from the right. So the left and right limit of the function do not coincide. That means the limit itself doesn't exist at 0. So the function is discontinuous at x naught is equal to 0. So the same idea you can see here, that g approaches 0 as x approaches 0 from the left. Similarly, g approaches 1 as x approaches 0 from the right. So limit x tends to 0, g of x does not exist. So there is the limit itself doesn't exist. So we get that the function is not continuous at x naught is equal to 0. And the example 4 says that if two functions are continuous at a point x naught, we can assert that their composition, if composition G, is also continuous at x naught. So suppose consider limit x tends to x naught f composition G of x. We have to show that limit x tends to x naught f composition G of x is equal to fg of x naught. That is our definition of continuity at that point, right? Uh, so we are taking the LHS. We have the LHS to be equal to limit x tends to x naught f composition G of x, which is nothing but f of G of x, right? So instead of taking LHS, just consider limit x tends to x naught f of x into G of x. By the property of the limits, you can write it as the product of limits. Limit x tends to x naught f of x into limit x tends to x naught G of x. And since f and g are separately continuous, you can, instead of limit x tends to x naught f of x, you can write f of x naught. Similarly, limit x tends to x naught G of x can be rewritten as G of x naught. So you get limit x tends to x naught f of x into G of x is equal to f of x naught into G of x naught, right? And also we have f of x naught into G of x naught is equal to fg of x naught. So you can treat it as just the product of functions. So the product of functions are defined like this. Fg of x is defined as f of x into G of x. That is how we can define that product of functions. So here we are saying that the product of two continuous functions will in turn be continuous. So that's the logic we are having. So what we are proving is, you can write it that product of continuous functions will be continuous. Okay, so this is the example 4 which we are seeing now. So you get since f of x naught into G of x naught is equal to fg of x naught. Finally, you are ending up with what we want, that is limit x tends to x naught fg of x is equal to fg of x naught. That means the product of continuous functions will in turn be continuous. So that is example 4. And also we in the earlier section, which is section 1.3, we had proved that if a function is differentiable at x naught, the function will be continuous at x naught. So the continuity can be inferred from the fact that a function is differentiable or not also. So example 5 asks us to show that whether the given function, which is equal to 3x squared by x cubed minus 2, is continuous at x naught is equal to 1, and we have to infer where will the function be continuous also. You can find d by dx of f of x. So d by dx of f of x is equal to d by dx of 3x squared by x cubed minus 2. You can use the quotient rule which we had seen in section 1.5. So here you get x cubed minus 2 into d by dx of 3x squared, which is 6x, minus 3x squared into d by dx of x cubed minus 2, which is 3x squared, the whole divided by x cubed minus 2 the whole square. So you get 6x raised to 4 minus 12x minus 9x raised to 4 divided by x cubed minus 2 the whole square. So from that you obtain 6 minus 9, so that will be minus 3. minus 3x raised to 4 minus 12x divided by x cube minus 2 the whole square. So where should we find the continuity? We should find the continuity at x is equal to 0. So find d by dx of f of x at x is equal to 0. So you simply substitute what we got here with x is equal to 0. So you get 0 divided by 0 minus 2 the whole square. So that will be 0. So you are getting that the function is differentiable at x is equal to 0. So we are using this fact that if a function is differentiable at a point, the function will be continuous. So since this function is differentiable at x is equal to 0, that will automatically mean that the function is continuous. So the function is continuous at x naught is equal to 1. And where will the continuity be lost? We know that if a function is a rational function, wherever the denominator is not equal to 0, we can guarantee the continuity of the function. So the continuity is lost when the denominator is equal to 0. So what you have to do, you can choose any point where the function is continuous, and those points should not be equal to x naught cube minus 2, which vanishes like that. So you have to say that it doesn't vanish. The function is continuous at every point x naught such that x naught cube minus 2 is not equal to 0. That means x naught is not equal to the cubic root of 2. So that's question A. And for question B, we have to check about the continuity of f of x is equal to square root of x square plus 2x plus 1 at x is equal to 0. So for that, first define h of u is equal to root u, and then define g of x is equal to x square plus 2x plus 1. So here f of x can be written as h composition g of x, right? So you get g of 0 is equal to 1. By definition, which is strictly greater than 0. And we have g to be differentiable at any x. And h is differentiable at u is equal to 1. So you get f is differentiable at x is equal to 0 by the chain rule. So the chain rule will enable us the conclusion that f is continuous, or else you can for a better picture, we have selected h of u to be equal to root u, and also h of x to be equal to x squared plus 2x plus 1. And then you are saying that f of x is nothing but h of g of x, which is true, because that will be h of x square plus 2x plus 1, which is nothing but square root of x square plus 2x plus 1. So you have kept that, and then you have to find the derivative. Here also we are finding the derivative. Derivative of f of x will be nothing but the derivative of h of g of x, which is by chain rule h dash of g of x into g dash of x, right? So here you can get that to be equal to you can calculate it properly as 1 by 2 root of x squared plus 2x plus 1 into the derivative of x square plus 2x plus 1, right? So you get that to be equal to 1 by 2 into root of x square plus 2x plus 1 into 2x plus 2. So that is 2 into x plus 1 divided by 2 into root of x square plus 2x plus 1, which is equal to x plus 1 divided by root of x square plus 2x plus 1. So you have to verify at which point you have to find the continuity. So here you have to find the continuity at x is equal to 0. So find the derivative at x is equal to 0. Just substitute for what you got here. So you get that to be equal to 1 divided by root of 1, which is 1. So you get that the function is differentiable at x is equal to 0. So that will in turn mean the function is continuous. So you can use the property that if a function is differentiable, the function is automatically continuous, and claim that. So that's how we proved or solved example 5, that is by using the fact that every differentiable function is continuous. And also in the second part we have used the chain rule for differentiation, and thus we understood that the function is continuous at x not is equal to 0. So that's all for today. So see you in the next part of this section. So thank you, and please do work out the lecture and have lecture notes with you to which should be submitted later. So thank you.